Moving on, we're now going to discuss greatest common divisors. So we'd better define what we're going to be talking about. Suppose I have a list of a bunch of integers. It's got k elements. They don't actually have to be different from one another. Okay, so I have at least 2, but possibly, as many as 12, 28, who cares? A list of a bunch of different integers. And a is another integer that is a factor of all of them. So if I have one number a, which is a factor of everything in a set S, then I say that a is a common factor of that set. It's a pretty straightforward definition. Almost always we'll only be considering sets of 2 integers, in which case we would just say that a is a common factor of the 2 integers, and in this case we've called them b and c. If a is a common factor of a set and there's no larger integer which is a common factor, then we say it's the greatest common factor, or greatest common divisor, abbreviated GCD, of the set. So not only does it have to be a common factor or a common divisor of everything in the set, it's the biggest of all integers that has this property, if such a thing even exists. So if we have a small number of elements in the set, there's pretty common notation. The greatest common divisor of 2 numbers is just notated as the 2 numbers in a parenthesis. Now, I'll admit this is somewhat an abuse of notation since this looks like the ordered pair b comma c, but in the context of elementary number theory, this is used all the time. It's the greatest common divisor of 2 numbers, or 3, this list b, c, d here. Beyond that, it doesn't really come up very much, and as I've mentioned, we're almost always going to be talking about the greatest common divisor or greatest common factor of 2 numbers, but we will be employing this parenthetical notation. So one common thing that comes up is students will say something like a is a common factor of b. Okay, but we have specified that this definition of being a common factor of a set only applies when you're talking of at least 2 or more integers. It doesn't mean anything to say a is a common factor of b. It's what we would say it's not even wrong. It's just meaningless. Okay, you can say that one number is a common factor of 2 or more other integers, but we just don't say that one number is a common factor of a second. We would just say a is a factor of b. We wouldn't say a common factor. Well, do such things even exist to begin with? So as I've mentioned, we're generally just going to be worried about finding the greatest common factor of 2 integers. And so from this point forward, that's what we're going to be looking at. So given 2 integers, is there even a greatest common factor to find? Are there any common factors at all? If so, if there are common factors, is there actually a biggest one? So here's a theorem. Given any 2 integers b and c, the greatest common factor does in fact exist, but that's if and only if they're not both 0. So if I look for the greatest common factor of 0 and 0, that doesn't even exist. But if I look for the greatest common factor of 2 integers that aren't both 0, maybe one of them is, maybe neither of them is, but they're not both 0, then the greatest common factor will exist. So as a proof, we know that it doesn't actually matter whether b and c are 0 or not. 1 is a factor of every integer. So 1 is a common factor of b and c. So there are always common factors of 2 integers. The only question is there a biggest one? Okay. We do know, however, that every integer is a factor of 0. So if b and c are both 0, then every integer is a factor of b, because every integer is a factor of 0, and every integer is a factor of c, because c is also 0. So every integer is a common factor, and there is no largest integer, so there's no greatest common factor of 0 and 0. Therefore, the GCF, or the GCD, of 0 and 0 does not even exist. But what if one of the numbers isn't 0? Let's suppose b is not 0. We're looking for the greatest common factor of b and c. We know that there are common factors to find because 1 is a factor of both of them, and we've now assumed that b is not 0. Well, since the absolute value of b is a natural number with the same factors, remember factoring doesn't care about positive versus negative, okay? So we also know for any a which is a factor of b, a must be a factor of the absolute value of b and therefore cannot be larger than the absolute value of b. So no integer larger than the absolute value of b is a factor of b at all, and therefore it can't be a common factor of b and c. Not even worrying about whether numbers are factors of c, if it's larger than the absolute value of b, it's not even a factor of b to begin with. So the set of common factors it includes 1, and it can't have anything larger than the absolute value of b, which is a finite number. So the set of common factors is a subset of the numbers 1 through the absolute value of b, and therefore is itself a finite set, and therefore has a largest element. So if at least one of the two numbers is not 0, then the set of common factors is non-empty, but also finite. If they're both 0, the set of common factors is all integers. But if one of the numbers is not 0, the set of common factors is a finite set, and therefore has a largest element, and therefore the greatest common factor exists. There are a few things we can prove immediately about greatest common factors. Suppose b and c are two integers, they're not both 0. Okay, in other words, the greatest common factor does exist. Then all of the following are true. The greatest common factor of b and c is the same number as if we had replaced them with their absolute values. In other words, if one of the two numbers is negative, or if they're both negative, just take their absolute values and work with that instead. We're never going to ask questions about greatest common factors of negative numbers thrown into the mix, because it wouldn't matter to begin with. Second, the greatest common factor is at least as big as 1. If b is not 0, then the greatest common factor is not any larger than the absolute value of b. If b isn't 0, then the greatest common factor is actually equal to the absolute value of b if and only if b is a factor of that other number c. So there's 4 things to prove here, and let's work through it. Well, for the first, we've already established that factoring doesn't care about positive versus negative integers. So the factors of b are the same as the factors of its absolute value, and similarly for c. So the common factors of b and c are the same as the common factors of the absolute value of b and c, and therefore the greatest of those two sets is the same. Okay, so generally, we're not really going to be throwing questions out here about finding the greatest common factor involving negative numbers thrown in, because it doesn't change the answer and it just adds potential confusion. Okay, so negative integers can always be replaced with their absolute value in the context of finding greatest common factors, that is. Moving on, we know that 1 is a factor of both b and c. So 1 is a common factor of b and c. Over here, we're finding the biggest common factor of b and c. Well, this is a particular common factor. This is the biggest of all common factors, therefore it's at least as large as the other one. Okay, now moving on to the other two claims. If b isn't 0, then the largest factor of b is itself in absolute value. We've already established this. Therefore, the biggest factor of b is its absolute value, so anything that's a factor of b and c cannot be any bigger than that. So any common factor is no larger than the absolute value of b, and therefore the biggest of all the common factors can't be any bigger than that. And the last claim, if the greatest common factor is actually the absolute value of b, well, if it's the biggest of all common factors, then it is one such common factor. Therefore, it must be a factor of both. So the absolute value of b is a factor of b, and then the absolute value of b would have to be a factor of c. But since factoring doesn't care about positive negative, if the absolute value of b is a factor of c, then so is b. But we have to work the other way. We didn't just claim if the greatest common factor of b and c is the absolute value of b, then b is a factor of c, but in fact the other way as well. So let's assume b is a factor of c. Factoring doesn't care about positives and negatives, so the absolute value of b is a factor of c. It's definitely a factor of b, therefore it's a factor of both, it's a common factor. Okay? Since the absolute value of b is one such common factor now, the biggest of all common factors can't be any smaller than one common factor that we found. But now I have the greatest common factor is bigger than or equal to the absolute value of b. We've already established it's less than or equal to, so it must be equal to it. Okay, so if and only if in this last claim. This is a handy thing that we will use from time to time. If the greatest common factor of two things is one of the numbers, then that number is a factor of the other. And that's if and only if. All right, moving on, another definition. Suppose I have two integers and the greatest common factor between them is 1. Then the two integers are said to be relatively prime. This is what it means to be relatively prime. The greatest common factor is 1. In general, if you have a set of more than two integers and the greatest common factor of the set is 1, then that set of integers is said to be relatively prime. There are a few things to be careful about with this definition. We would never say that a number is relatively prime. Okay? In order to apply the term relatively prime, you're talking about the greatest common factor of a set being 1, and remember that set has to have at least 2 elements. So the definition of relatively prime only applies to 2 or more integers. Note, we have not defined what it means to be prime. We've only defined what it means to be relatively prime. It actually turns out to be easier to define this first. Okay. As with greatest common factors, we're almost always just going to be talking about 2 integers when it comes to relative primality. So let's look at an example. Compute the greatest common factor of 42 and 20. Well, the most straightforward way to do this is to list out all of the positive factors of each term. Here are the positive factors of 42. Here are the positive factors of 20. What are, therefore, the common factors of 42 and 20? Well, the largest number that's in both lists is 2. So that's the biggest number. That's a factor of 42 and also a factor of 20. Therefore, that is the greatest common factor. Another example. Show that the set 6, 10, and 15 are relatively prime. Well, the factors of 6, 10, and 15 are, here are the factors of 6, here are the factors of 10, and here are the positive factors, at least, of 15. Since we're talking about greatest common factors, it only is necessary to look at positive factors. Well, here are the factors of 6, 10, and 15. The only number that appears in all 3 lists is 1, so the only common factor of that set is 1. So this triple of numbers are relatively prime. But we should be cautious. If I was only looking for the greatest common factor of 6 and 10, I'd be looking at these 2 lists, and I'd see that 2 is the greatest common factor of 6 and 10. If I was only looking between 10 and 15, I'd see that 5 is the greatest common factor of 10 and 15. And between 6 and 15, we have 3 is the biggest common factor. So as pairs, they are not relatively prime, but the triple is. So you have to be really careful when applying this term, relatively prime. Relatively prime applies to a set of numbers, and if you change that set, you might change whether they're relatively prime or not. In this example, what we've seen is that this trio of numbers are relatively prime, but any pair I form from them are not. Okay. That said, we will almost always, from this point forward, be talking only about pairs of numbers when it comes to greatest common factors. And in the next video, we're going to start learning more convenient techniques for computing the greatest common factor.